Okay. So when we talk about nonlinear equations, what comes to mind? I'd love to hear from those of us in class. What comes to mind? We play with a lot of nonlinear equations, in our day-to-day engagement. So can we get feedback from those of us in class? I think I can see. Go ahead, please. Yeah, go ahead.
Yes. These are equations that you cannot use linear. There cannot be the answers cannot be arrived at using linear solutions.
Okay.
They are in form of differential or integral functions.
Okay. Awesome. So can we get another view?
Yeah, these are equations. Yeah, these are equations that has to do with.
Go ahead,
hello, sir.
Mr. Festus. Yeah, go ahead.
These are equations that has to do with either curves or it involves the use of graphs.
Okay, nonlinear equations. So meaning you just mentioned that if we have to take this for assessment, we have to ensure we provide graphs, right?
Yes, sir.
Okay, yeah, you're right. Okay, that's awesome. It involves the use of graph. Now, I have a follow-up question to Engineer Festus before I take Engineer Asimi. Now, if we have to use graph for nonlinear equations, how about linear equations? Don't you think we also need graph?
Yes,
should be a straight line graph.
Both of them need graph, but it's just the pattern of results.
The
linear should be a straight line graph, while the polynomial
the other one is
curved.
Okay, it's curved. But in practice, what can we say is linear or nonlinear? Are all differential equation problems nonlinear? I think I just got you there. We'll be talking about differential.
No.
Okay, yeah, no.
Not all.
Not all, because we also deal with some linear differential equation problems. But what makes this nonlinear? Okay, let's hear from Engineer Simi. Go ahead, please.
Nonlinear equation are those equations that have a maximum degree of 2 or more.
I can hardly hear you. It's cracky.
Okay. Nonlinear equation are those equations that have degree more than 2 or more, degree 2 or more. So at least we can have more than 2 degrees. So for example, when we have x squared plus y squared or x cubed plus you can derive like that.
Okay, so we have some degree, to the model representing it, either a polynomial or whatsoever. Awesome. Now we have Eroms. Can you go ahead, please?
All right. My contribution is for nonlinear equations. They are equations that have powers. Their powers is always from 2 and above.
Okay.
And at the end of the day, the independent and independent variables will always be at least 2 values. While for linear equations, the power is usually 1, and both dependent and independent variables will always have just 1 value.
Yeah.
Thank you.
Thank you very much. Now, you've all given beautiful contributions and you're all correct. Okay, so I think Eroms want to drop his hand, right? Yeah. So you can drop your hand. Yeah. So now, I have another question to ask. Why do we have to study nonlinear equations as engineers? Because I understand you're all engineers, you've been practicing for years. So why do we have to study nonlinear equations? What's their significance in our study? Go ahead, please. Yeah.
To be able to model some system, because some of the systems that we are working on, they are in nonlinear regions, so we need to be able to model it. I think that's why we need the nonlinear equation.
Okay, so can you give us an instance, a practical instance? where we have to deal with non-linearity in the system?
Well, I can say, for example, if you are trying to work on amplifiers, some amplifiers, so depending on the region. So if it's in the non-linear region, so we want to model it using the non-linear equation. So I think that's how we can relate the non-linear equation of this mathematical model to what we do in the amplifier. So I'm just speaking for the amplifier, like a system
Okay.
amplifier system.
Yeah, you seem to have electronics background, right?
My option is electronics, but I think it's a
Okay.
general thing that we are doing. So
Yeah. I know, but when we now go way into our discipline, some of us we begin to play less with amplifiers. But I know amplifiers is all part of what we get to do. Okay, we have Engineer Simi. Can you go ahead, please?
Okay, thank you very much. So for most of the time we have non-linear equations. Those devices like those that take multiple inputs and give them multiple outputs.
Mm-hmm.
So most systems actually which of them taking lot of inputs and also give outputs. So I think that where we have most of this in like non-linear equations.
I'm struggling to hear you clearly. Can everybody hear him clearly? I want to be sure. Yeah, it's really cracky, you know. Is there any way?
I don't know. Whatever.
Yeah, and what you just said, I feel is very important to us. I don't know if there's any way you'll be able to probably make your audio a little clearer. Okay.
So
Go ahead, Samuel.
okay, good. Thank you. Now, with respect to power systems, there are some kinds of loads we call non-linear loads, and you know the proliferation of non-linear loads is actually increasing. So a practical example would be if you know
the network's cracking again. Oh my goodness.
respect to charging rate is non-linear. That's why you see all this fast charging that you can charge from 0 to 80%, but you can't charge from 0 to 100% because immediately you get to 80, the charging rate becomes very non-linear, and it's just an example in power systems.
But is there a problem with that? Is it acceptable, or does it give us anything to worry about, or is just a normal way of? Can we accept that as a normal mode of operation, or we need to worry about? Or
yeah, it's normal with that the charging station, the EV charging station operates, and even the batteries, especially lithium-ion batteries. Now the thing is, there is still research going on how to accurately model
the linear.
Yes, that non-linearity.
Yes, exactly. To linearize the.
Yeah, that linearization is a form of approximating
yes,
non-linear characteristics of the
almost.
Okay, so if I get what you're saying, it means the non-linearity is unacceptable.
Yes.
Yeah, if you want to linearize it, it means it's something we don't want in our system, right?
Yes, sir. Then also when we want to talk about in power system, transient analysis.
Okay.
Transient I thought somebody is talking. Yes, in transient, most of these transient into our power systems, they don't follow the because transient comes into when they don't follow the regular fundamental frequencies, and most of these harmonics they are always in octaves. So that means that how do I say it? A multiple of the fundamental frequency. You don't follow linearity. So we need to attend to this issue so that transient response won't disturb our system or destabilize
our system.
Power
Okay.
systems.
Okay. Thank you very much. Now we have Oferuche. Can you go ahead, please?
All right, sir. Since most systems in engineering, they are nonlinear because they involve interactions between multiple variables. And because of that, they can change in maybe simple or constant manner. So let's say in circuits now with semiconductors, in circuits with semiconductors or diodes, there's a relationship between voltage and current. That relationship there is nonlinear. That's what I wanted to say.
But is that relationship you just mentioned that is nonlinear, is it desirable?
Depends. It could be.
Okay. Okay. Perfect. Thank you so much. Yeah, it could be. Okay, you can drop your hand, madam, and nice contribution from you too. Now, the idea now is nonlinearity in our systems. Okay, is it desirable? And Oferuche just said, well, it depends. And some other colleagues we have here just mentioned that, well, in some of our systems, we always find a way to linearize. And most of our loads are nonlinear. And it means that the nonlinearity condition in our systems, engineering system, breeds some level of instability. Okay? And the question now that arises is, how do we resolve this stability problem? So I know most of our colleagues in power systems and all of that, they love to research in stability analysis, right? So I think it's one area they've been able to figure out, the easy way out. Now, that is why we want to look up nonlinear equations, okay? Because we want our systems to be stable. And for our systems to be stable, there's something we call the characteristic equation. Do we still remember this? Do we still remember this?
Yes, sir.
Now,
Yes.
this characteristic equation, what does it do in our systems when analyzing our systems?
It gives us a characteristic value to characterize the system.
So it means, yeah, which is what?
It gives us the value of the agent value, which characterizes the system.
Exactly. And that eigenvalue, the eigenvalue you just mentioned, is the root of the equation. And this is the same root that forces the function to 0. That's the point. So when we have to deal with nonlinear equations, our target is the root of that equation that forces it to 0. And once we are able to identify that root, we can say we have been able to establish the value of the eigenvalue. And the eigenvalue is that property that characterizes the system. And then with that eigenvalue, we should be able to tell if the system will be stable or not. And this brings us once again to the poles, right? And then there is a place in the x-plane we want the poles to be to ascertain the stability of the system. Now, that is the idea, okay? So when you end up modeling the system, and you've been able to come up with the exact model that characterizes that system, should it be nonlinear, which we know in most of our practical systems is going to be nonlinear, then the next thing you want to do is to evaluate the roots of that equation. And once you are able to evaluate the roots of that equation, we are done. Because the roots will help us to analyze, predict, and even optimize the properties that characterizes that system. Okay? And we know that when we have negative roots or negative real parts, or if the roots have negative real parts rather, then we say the system is stable, right? And just like Ophel Richer just mentioned, yeah, when we are able to, for instance, let's say we are able to evaluate some values of the current and voltage, unknown values of current and voltage in nonlinear circuits, like you have in your transistor models, your power electronics, and all of that, then we have been able to evaluate the roots of that system, which can help us linearize, right? And once we're able to linearize, we say our system is stable. So we always want to figure out the operating point where the system is linear. And even in signal processing, these same roots help us to find frequency components in filter design. Then we can talk about Fourier analysis. And Engineer Joel made mention of harmonics, right? So we want to get rid of those harmonics because we don't need them in the system. They just make our system unstable, okay? So if we are able to target the fundamental frequency value, which we can say is one of the roots of that particular equation, we are done. Then we can filter out whatsoever we have left, and then we can ensure the stability of our system in practical terms. Okay, so our target now is for our nonlinear equations. Our target now is, well, what are the roots of this function that forces it to 0? Okay, and you've all been able to establish the fact that, well, most of the systems we deal with, from control systems to machines, even the magnetic flux in transformers and motors are all modeled using nonlinear equations. You can talk about the torque and speed relationship in your induction motors. They are modeled using nonlinear equations, okay? So quite a lot that we have to deal with. You see that we just want to figure out a way to deal with these non-linearities. And in dealing with these non-linearities, and I say, well, what are the possible methods for evaluating the roots of this equation? And you already mentioned too that, well, this is not something we just want to begin to solve analytically, is because we end up running into an iterative process, okay? And we'll continue to repeat this process till convergence. And we say the system have that the iterative process converge if it's as close as possible to 0. Okay? Okay. So any questions so far before we move on to solve a few examples and then call it a day? Any comment? Probably you have an observation, you want to make an additional comment or something, so we know. Or can we move on? I'd like to be sure you are still with me.
Yes, sir. Let's move on.
Okay. So
Yes,
now
sir, we
that,
can move on, sir. Yes,
okay.
sir, we should move on.
Okay, thank you. So now that we've been able to establish this fact, so I wouldn't want you to continue to relate with whatsoever we drop or put on this whiteboard as a nonlinear equation as some equation. I'd love you to begin to relate with such equations relative to your discipline. Okay, so probably we are just trying to model the semiconductor device. Okay, probably this is that power system unit. Okay, this is the nonlinear load. Okay, so that we now see why we have to do this. The bottom line is we want to solve the characteristic equation. So for those of us in control and the likes, you want to see every nonlinear equation we drop from now as some characteristic equation, okay, for which you need to evaluate the poles to analyze the stability of the system. Okay, so I think we take things that way. So we can now say formally that the roots of this nonlinear equation, f of s being the same as 0, cannot in general be expressed in closed form. Okay, so it means that even when this is possible, the expression is often complicated. And that also makes it, you know, impractical or impracticable, you know, when it comes to implementation. So for us to be able to solve these nonlinear equations, we now have to figure out an approximate method. Okay, and these methods, like we mentioned earlier, require some kind of
incoming voice call from +23.
Require some form of iteration. Okay, so it means that we have to first of all figure out an initial approximation. Okay, so once we figure out this initial approximation to the roots, then we now come up with a system of roots, S0, S1, S2, and all the way. And while we are iteratively evaluating or estimating these roots, we also test for convergence within a certain interval for which S lies within a range, say AB, okay? And if it doesn't converge based on the tolerance defined, then we now come back again and begin the process, okay? So this really makes solving nonlinear equations a little cumbersome and, you know, will I say difficult? Probably something that just bores us, you know, and then we want to rely on some of these tools like MATLAB, Python, and the likes to just help run through this iterative process, okay? And till we're able to get good approximation. So it means that till you get a reasonable approximation, you just continue to repeat the same process over and over and over and over again. And some of the methods we use for this are, let's come back to this. The try and error method. We also have the closed domain methods. This is usually referred to as the bracketing method, right? Yeah. And then we also have the open domain methods. So these are literally the methods we could use to address this nonlinear equation root finding problem. And when we talk about the try and error methods, we simply want to guess the root. Say S is the same as alpha, and then try to evaluate f of alpha, for which f of x had been given already. And if f of alpha is close enough to 0, then we quit. So if this should tend to 0, then boom, we are done. Okay? Now, if not, then we guess another alpha. and continue until alpha is close enough to 0. And this approach is acceptable, okay? It's very, very acceptable. And it's pretty straightforward, you know? But for the closed domain methods, like we also call the bracketing methods, they are methods that literally starts with 2 values of x, okay? And then it will now bracket the roots such that x is now the same as alpha. And this systematically reduces the interval, okay? So let's assume we have S0, then we have x1. So it finds a way of bracketing this probably by taking the average so that x will now be the same as alpha, which is an interval, a root within this interval, okay? And then the idea is that we want to always trap the roots within this interval. And the methods we are going to look at in this are the bisection method, which is the interval halving method. And also we'll look at the regular Falsi method. Here we call it the force position method. Okay, so we always want to, it's more like the 2 given points now serves more like boundary conditions, right? So we want to figure out the root within that domain. So bracketing models or methods are pretty good. They are robust in that they are guaranteed to obtain a solution since the root is trapped within that closed interval, okay? But the challenge is they can be slow to converge, right? And then we also have the open domain methods, you know, and these methods do not restrict the roots to remain trapped within the closed domain or interval, okay? And then they are also not as robust as the bracketing methods, and because the bracketing methods are sure to converge, but the open domain methods could diverge, okay? But notwithstanding, they literally use information about the nonlinear function itself to refine the estimate for the next iteration, okay? So they are really, really efficient, more efficient than the bracketing method when we want to talk in terms of the reliability of the method, okay? And some of the methods we have here are the fixed point, iterative method. Then we also have, you want to say something, please? Okay, we have Newton's method. We have the secant method, and we have the Muller's method. Okay, so these are the methods we'll look through. We'll just run through them quickly, and then we'll call it a day. But I consider them to be pretty simple and straightforward. These are things you must have been playing with for a very long time. Okay, so let's look up the formulation for this method one by one, and then we'll see what more we can do. So, well, I already mentioned for the regular Falsi, or better still, force position method. So here, the method literally combines the bracketing features of the bisection method, okay? With some linear approximation of the secant method. So we are looking between the bisection and the secant, and it converges faster. This is faster than the bisection method. but it may stagnate at some point. So if, for instance, we are given two initial guesses, say A and B, such that f of A dot f of B is less than 0, then we have to compute the next approximation, C. As C being the same as A minus f of A times B minus A over f of A, f of B rather, the subsequent point function minus f of A. And here we want to update A or B based on the sign of f of C, okay? And then we want to repeat this till it converges. It's quite an interesting method. So why do we want to do this? So for instance, we are getting a negative value. So we want to move away from that negative value towards a positive because we need real positive value. So we want to move away. So if x is now negative, so we want to check between this point and the next positive root, okay? So we always move in that direction. So depending on the sign, then we keep, moving towards that part where we are sure we are going to get a real value for our root, a non-zero value, is a non-zero, no, not non-zero, a positive value, not a negative value. The negative value is less, than 0. So that's why once we have these 2 points, then we want to compute this function. So, and if it's less than 0, then we have to compute the next value. Well, we'll see how this works. But I understand you already know how it does anyway. Then another method we want to look up the formulation is the bisection method. So, well, this method systematically narrows the interval where the root lies, okay? So, like we said, it's simple, it guarantees convergence, only that the convergence process may be very slow. And now, if we are given two initial guesses, say A and B, such that f of A times f of B is less than 0, then the root C is computed as C being the same as the average value between the roots. And once we do that, we now want to check if f of C is the same as 0. Now, if this condition is true, then it means that C is the root. So otherwise, we have to update, all right? And then in updating, if f of A times f of C is less than 0, then we set the next point to B to be C, or better still, if f of A dot, no, sorry, yeah, B this time will be BC, because we already treated A, C. So if f of C dot f of B is less than 0, then we want to set A to be equal to C. So we want to repeat this until, we get convergence. Now, the next formulation is going to be now we've looked up the closed methods, so let us look up the open methods. the Newton-Raphson method. So this method literally converges quadratically, okay? Near the root, okay? So if the initial guess is close. So the challenge in using this method is that it requires a computation of derivatives. So we don't just play with the function, we now have to figure out the first derivative of that particular function. And, you know, it may also diverge if the guess is poor or if the first time derivative function is not approximately 0. So in this case, we are literally starting with our initial guess. S being the same as S naught, or better still, let's just leave it as S naught. Then the next approximation will now become the next approximation. Will now become Sn plus 1 being the same as Xn minus f of Sn over the first time derivative of Sn. Okay, so this is the first derivative of this function evaluated at Sn. So here, we now want to check for convergence if Sn plus 1 minus Sn is small, it's close to 0. That is as close as possible to the predefined tolerance. So once we get something within that tolerance and there is convergence, then it means there's convergence, then we are good, okay? Now, that's that. Then another method we'll consider here, okay, is a secant method. We have about 4 of them we'll look up. So we have secant method. In this case, unlike the Newton-Raphson method where we need to evaluate the first derivative, here we don't need to evaluate any derivative. So it uses the finite difference approximation technique, okay? And this is also faster in terms of convergence when compared with a bisection method, but it's slower than the Newton-Raphson method, okay? And well, it may fail if the function is not well behaved also. And I understand that most of your past systems activities, you want to use Newton-Raphson. So we are going to support that today, why you should not use Newton-Raphson, okay? So we want to start in this case with 2 initial guesses. Say S0 and S1. And then the next approximation will become S of n plus 1 will be the same as S of n minus f of Sn times Sn minus Sn minus 1 over f of Sn minus f of Sn minus 1. So that's the formulation. And then the next now is the fixed point iteration method. But this is pretty straightforward, fixed point iteration method. Now, in this case, the convergence depends on the function g of s. Convergence depends on g of x in this case. And should the first derivative of x, the modulus of this be less than 1, so the method converges, okay? If this is the same as 1 at that given root. So what this implies is that a poor choice of this function will make the system or the root finding to diverge. And the formula is literally to just rewrite f of x being the same as 0 at x being the same as g of x. And then we iterate using xn plus 1 being the same as g of x. We'll see how this works with a simple example. Okay, it's pretty straightforward. You do not need, there's no much headache. Now, one interesting method I really like is the Muller's method, or Muller's method. And the reason I like this method is that it's literally an iterative method for finding roots, okay? When we have f of x being the same as 0. Okay, so this method literally extends the secant method we just mentioned by using a quadratic polynomial. Rather than a linear one, okay? Because in secant, we use linear polynomial. So, and this literally makes it faster and more robust in terms of handling complex roots, okay? So here, we can use the Muller's method to evaluate complex roots. This is one thing the Newton-Raphson's method cannot do. That's why I said, well, now at some point, you now will, in case you're conducting your research and all of that, and you get to figuring out the roots of your nonlinear equation, oftentimes the method that comes to mind is Newton-Raphson. Let's try Newton-Raphson. Yeah, you're going to get something going, but there are, in most of our practical systems, no doubt, we run into complex roots, and the Newton-Raphson's method cannot do that. So you'll be needing the Muller's method, so you are able to evaluate the complex roots or complex roots. So, so by definition, if we are given initial estimates, so here we have initial estimates, S0, S1, and S2. Now, Muller's method literally approximates the function f of x using the quadratic polynomial. P of x being the same as a into bracket s minus x sub 2 squared plus b into bracket s minus s sub 2 plus c. Okay, so now I need some space. So we're writing Muller's method. So we've identified the initial roots, x1 and then s2. And then we have also mentioned the method used to approximate the function, which is the polynomial function, the same as a x minus x sub 2 squared plus b into bracket s minus s sub 2 plus c. And here, we now have to evaluate the coefficients, okay? So how do we compute A, B, C? Now, we first of all figure out the step size between x0, x1, s2, such that h sub 1 is the same as x1 minus x0, and then h sub 2 will be the same as s sub 2 minus s1. And once we do that, we now evaluate the difference. Delta 1 be the same as f of s1 minus f of s0 over x1 minus s0. And for this, that would be delta 2, f of s2 minus f of s1 over s2 minus s1. And then the coefficients follows directly such that a will be the same as delta 2 minus delta 1 divided by H2 plus H1. And then B will be the same as A H2 plus delta 2. And then C will be the same as F of S2. Okay. And now the roots of the quadratic equation, because we already have a quadratic polynomial, so the roots of that can be evaluated by x sub 3 being the same as x sub 2 minus 2c divided by b plus or minus square root of b squared minus 4ac. Boom. And then here, once again, the sign is chosen to ensure that the denominator is maximized to avoid numerical instability, okay? And so that now we're going to look up an example to see, you know, and if there is no convergence, by the time we compare, we take the modulus of the difference between the the approximated root and the previous root. If it does not, if it's not as close as possible to the tolerance value, or is greater than the tolerance value, then we have to perform all of these operations again, everything you see on the board, then in that iterative process. So the good thing about the Muller's method is that it's, in terms of convergence, it is faster than secant and the regular Falsi method. It can equally handle complex roots directly, and it also does not require derivatives, unlike the Newton-Raphson's method, okay? Only that it is slightly more complex when calculating, okay, relative to the secant method. And well, it may converge to a complex root too when a reroute is required. So you want to be sure what you want in your approximation method. And another downside is that it is highly sensitive to initial guesses. So I think this is about it when it comes to formulating all of these methods. So I'll just run through brief examples, you know, and then wherever we stop, we assume that you can take things off from there. So let us start with the bisection method. So let's assume we have x cubed plus 2x plus 2 being the same as 0 as the function. And here we have the roots to be between 0 and 1. Okay. So we want to find the root to any decimal place using the interval halving or bisection method. So when we talk about bisection, like we mentioned earlier, so we are literally saying this is interval halving. And we already know why the solution of your nonlinear equation has to do with finding the roots, okay? So we want to find the root such that we are able to tell, depending on what you are doing, we're able to characterize the system, okay? So we want to find a root where this equation is the same as 0. And should that become the characteristic equation that characterizes the system you are modeling, then the roots becomes your eigenvalues. And you know what your eigenvalues are, okay? So they provide all that you need to characterize the system because they are just that value that is tied to the eigenfunction of the system. And in system synthesis, that is what we need to just tell or to inform us as to what we need to develop or design the system. Is it an integrator? Is it a differentiator? That will now tell us, do we need a capacitor or an inductor? Okay, so depending on what it is, so we can now move from the characteristic equation to now synthesize the system to now come to the components we even need to develop and design the system. So the roots of your model is very, very important in terms of modeling or characterizing or telling the behavior of the system. And with the same roots, we are able to also tell the stability of the system. And if a system must be well behaved, it must be Bible stable. So it means bounded input, bounded output. Okay, so we don't want something that will deviate. So we don't want systems that will act in a manner that will say, well, this is not well behaved. So we want systems that are well behaved. So we want roots that will fall within the domain that will say this is stable. Okay, so there are a lot of tools or techniques you can use to evaluate the stability of the system. Then if you go way into evaluating the poles of that characteristic equation or the roots, which we can now say are the poles, then you can also tell if the system is observable, if it is controllable, and the like. So everything that has to do with characterizing the performance and the behavior of the system all falls within these roots. And so we need to figure out a way to pull off these roots by figuring out an approximation to that exact, though we cannot figure out the exact root. So since we are going through an iterative process, so we just want to get something that is as close as possible to it. So now that we have this, I want to perform interval halving. So we already know that f of s, f of s is the same as this. So we have these two intervals. So we want to figure out f of naught for the first interval, which is 0 cubed plus 2 into bracket 0 plus 2. This will give us, okay, sorry, I think I want to change this so that I don't have a positive. So let's make this minus 2, which will give us minus 2. Now for f of 1, we now have 1 cubed plus 2 into bracket 1 minus 2. So this would be what we have here. So that's 3 minus 2. So that's going to give us 1. So we can now plot this to see what we get. And mind you, why do we want to evaluate these roots? So we say we have a root when it crosses the x-axis. So if it doesn't cross the x-axis, then it means there's no basis for convergence. Okay, so now we can plot this. So we have minus 2 at this point. Then we have 1. This is for x. This is f of x, right? So when x is 1, then this is minus 2. So we have something like this, and then we can now plot when f of naught is the same as 0, okay? So our graph is going to look something like this, okay? Where this is 1, for instance, okay? So you can literally plot and all of that. So we want to get our initial guess. So our initial guess here will be 0 plus 1 over 2, like we defined or described. So this will give us 1 over 2, which is 0.5. So we want to figure out f of 0.5. So what do we get here? 0.5 cubed plus 2 into bracket 0.5 minus 2. So this will give us minus 0.875. Okay. So when x is 0, this is minus 1, minus 2. And then when s is 1, when s is 1, this is 1. So we have these 2 points. So 0, yeah. I can see one hand up. Deolu John, go ahead, please.
Okay, all right, yes. Can you hear me, sir?
Go ahead, please. Yeah.
All right, thank you so much, Doctor. Yeah, please, on this graph, I just wanted to be sure if you're on the same page, because looking at when x is 1, right? So
when x is 1, f of s is 1, this is 1, x is 1, f of s is 1. So we plot this. When f of s is 0, when f of s is minus 2, s is 0. So, okay. So these 2 points join, right?
Okay, so
this is 0, this is minus 2. So it crosses the x-axis, so it means there is a root.
Okay, so I now need to understand this computation that follows, where we place x equals to 0 plus 1, 2. So how did you come about that computation?
This one, x plus
Yes,
1.
the one x equals to 0 plus 1 divided by 2.
Okay, yeah, that's the interval halving. That's the bisection. So recall when we try to define what this secant method is, and we try to define the formulation for the secant method. So we literally said, well, for this, this bisection rather, we've not got into secant. So when we talked about the bisection method, we said this finds the alternative root. So the next root we want to use for approximation can only be derived through interval halving.
So what in terms of, is it for all solutions that we're going to use this 0
No,
plus
no,
1?
no.
So what in terms of what to use?
Yeah, now we have these intervals. So these are the two intervals we have. So we have to take the average of these two intervals, and 0, 1 were given. Okay?
Okay.
So these intervals were given. And if you remember, we said for the bisection method, the root lies between two possible roots, right? So usually you'll be given two roots, A, B. Okay? Because if you recall the definition we gave, we said given two initial guesses, right? You were given two initial guesses, A and B. And these are the two initial guesses, right?
Okay, it's clear, sir. Thank you so much.
So once we plug, yeah, you're welcome. So once we plug that into this, then this is what we get. But now you realize that we have a negative value for our function. So we can also plot this, okay? So at x being the same as, let's say 0.5, then we are getting, probably at this point, we have minus 0.875. So it means this point is somewhere around here, right? Yeah, it's still negative, okay? So we need to figure out a root, really, because the root must cross, is that point that crosses this x-axis. So you now see that the root that approximates this, that crosses this axis at, x being 0 is the root we are literally trying to figure out. So that's why we are trying to figure out a root that is as close as possible to this, but not a negative value. So we prefer a value that is around this axis, that is around this positive axis. So now we are literally moving. So we've moved from this point. We are somewhere around here. We are getting closer. Okay, so, but we may not get to this point, but we may exceed it and come somewhere around here. I don't know if it makes sense. Hello?
Yes, it does. It does.
So, but the root of interest is this root, right? That's the root of interest for which x, Now, well, that's fine. So we can now move on. We iterate again, right? So now that we have this, f of 0.5 is the same as negative 0.875, and we've plotted that. But we now see that this is a negative value. Why f of 1 is a positive value. Okay, so it means that we have to now move away from 0. So if we now want to figure out the next point, so we don't want to take the interval. Now, this is what I mean. In this case, we now have 0, we have 0.5, and then we have 1. Okay, now, at this point, we got a negative value. So it means that if we should take the average of these two, say 0 plus 0.5 divided by 2, we are bound to get another value within this negative range. So instead, we want to choose this. Okay? So for our next interval halving, we are now going to use our x to be 0.5, this point, and 1 plus 1 divided by 2. which would be 1.5 over 2, which is 0.75. Does that make sense? So then we now figure out the function at 0.75, which would be 0.75 cube plus 2 into bracket 0.75 minus 2, which will give us minus 0.078. This is still negative. Okay, so it means we now have 0. Let's change the color. It means we now have 0. We have 0.5. We have 0.75. Then we have 1. So this, again, at this point, the function is negative. So we cannot take these 2 points. Okay, that is where, you know, if you look at the condition such that the product of this and this should be less than 0, right? So that's what we are literally trying to play with now. So it means that our next interval halving will now be x being the same as 0.75 plus 1 divided by 2, which will be 1.75 over 2, 0.875. So we want to check again, f of 0.875 will now be 0.875 cubed plus 2 into bracket 0.875 minus 2 will be the same as 0.4199, right? So this is positive. Now, when we plot, you now see that so far, let us pull up this detail. We have at 0, when s is this, and f of x is this. At 0, we got minus 2. At the next point, 0.5, we got minus 0.875. Then at 0.75, we got minus 0.078. Then at 0.875, we got a positive value, 0.419. So at 1, we equally got a positive value, 1, right? So it means that when we plot this graph, f of x, and this is x, so let's say this is 0.5, this is 1, and then you have, say, 0.75, then say we have 0.875. So this is minus 2. Then so this is what we got here, and this is what we got here. So that's what we got here. Then at this point, so I think we plotted something around here. Then at this point, we also plotted something around here. But at this point, we plotted something around here. So it means this our graph goes something like this, and like this. So this is a point that is literally close to this. So we can stop. Okay, we don't, because if we now take between this interval to this interval, we'll be going too far away from 0. I don't know if you get what I mean.
Yes.
Okay? But now we can still get a point around this axis, because this is at 0. We got here 0.419. So it means that between these 2 points, we can still get something closer to this point. So we don't need to take our interval between 0.875 and 1 again. So we now want to take x between 0.75 plus 0.875 divided by 2. So this should give us 1.625 over 2, which is 0.8125. So 0.8125 should be somewhere around here. So now if we find f of, let's change this color. Now if we say f of 0.8125, it is 0.8125 cube. I think what's the next thing? It's plus, right? 2 into bracket 0.8125 minus 2. So we're going to get 0.161. Okay, so that's even a better approximation, which is going to be somewhere around here. Do you get the point now? So we can continue, we can go on, and now take this point again, because now we have a point in between this. So now we are working backward. Okay, so we can even try again between that point and this point till we get an accurate route that lies between, you know, this particular point and this new point. Does it make sense? Hello?
Yes.
So you
Yes,
now
sir.
see that the interval halving method just goes back and forth in order to find that approximation. Okay. Now, if that is clear, then we can.
Now the question is, Doctor.
Okay, go ahead.
Okay, at what point do we now stop our approximation?
Yeah, when it converges. So the bottom line is we want to figure out a route that forces this equation to 0.
Okay.
So it is not 0 yet, but it's getting closer to it. So we don't want something that will be less than 0. We don't want something that will be greater than 0. We want something that is somewhere in between. So we are going to continue with this iterative process till we get something that is as close as possible to 0. That's why it's iterative. That's why we want to rely on algorithms to perform this iteration for.
So,
Yeah. Okay, go ahead.
How close to 0 should it be?
As close as possible.
Is there a value for it?
Well, there could be a value for it depending on what you are designing. That's why at some point we define a tolerance value. Okay, so depending on your system requirement, there is an acceptable threshold for performance. Okay, that's why we say that the reliability of a machine cannot be 100%. It can be 1, but it can be as close as possible to 1, right? So in as much as the reliability is not the same as 1, it means that the system is not foolproof. It's not 100% stable. I don't know if you get what I mean. So,
Doctor, sir.
Yeah, go ahead, please.
Doctor, sir.
Go ahead, please. We can hear you.
Can you hear me, sir?
Yes, I can hear you.
Yes, sir. Now you, assuming that you do the next halving, and you now get back to negative.
So we now take that new negative. So we now take the root of that new negative value to see if there is a positive value to the other end for our next.
To the other end.
Yes.
And yes. Okay.
So you are literally going back and forth till you get a good approximation. Now there's Olani. Go ahead, please, Olani.
Yes, sir. I want to confirm, what method did we use for this equation?
This is we are still on bisection, I guess. Yeah.
Bisection.
Okay. That's interval.
Right. Thank you very much, sir.
Halving. Yeah. Okay. I don't think we have so much time anymore, so I think I will stop where I can stop, and I will leave the rest for you guys to solve. I think that would be a good deal. Okay, so let's look
Doctor,
up.
please, before you proceed,
Okay, go ahead.
Using this method, there is something I know personally, that you are going to do your iteration to a point whereby the previous answer you got from the average will now be the same with this last answer. Then you stop. That is what I know. I don't know if that.
We are going to come to that too. Now, when, for instance, what we now continue to get 0.161, 0.161. So no matter what we do, we get 0.161. Then we say, well, at this point, it has converged.
Exactly, sir.
So there is no amount of iteration you will perform that will make it go beyond
that.
Okay? But there's also a caveat, okay? Because there is the level of iteration you will still go, then the system will not be well behaved. It will diverge. And that is why when you run your algorithm, you define the limits of iteration. So after 1,000 iteration, after 500 iterations. So if we should leave it in an infinite loop, it will diverge again. You could try it when you run your simulation.
All right, sir.
So that's the essence of tolerance, especially when you are running models and then you have to develop an algorithm. You don't want an algorithm that will run infinitely. You don't have the processor to deal with such processing. So you want it to iterate to some level, and if there is no convergence, it should terminate. You get the point, because you want to preserve a whole lot. There's a lot of electronics going, electronic processing and all of that. So you don't want to blow out your processors, okay? So at some point, you want to terminate the iteration if it doesn't converge after a number of iterations. That's what you do in your programs, right?
Yes, sir.
Yeah. Okay. Now let us look up the regular Falsi. Now let's assume we have f of x being the same as x cubed minus 2x minus 5. Okay. So here we want to find the region within the graph the root lies. Okay. And going by this, what do? We just go by some form of assumption. So this is regular Falsi. So let's assume f of naught, for instance, to see if we are going to find the root. So that would be 0 cubed minus 2 into bracket 0 minus 5 minus 5. Oh, this is a red flag, this negative value. So we can't use this. So let's go again for 1 cubed minus 2 into bracket 1 minus 5. So what do we get here? This would be minus 6, right? Is it? Yeah. Minus 7, then 1 minus 6. This also a red flag. Then we'll keep going. F of 2. 2 cubed minus 2 into bracket 2 minus 5. So this is going to give us negative 1. Okay, we are getting close to 0. So I think there's hope. It is dropping now. So let us try for 3 when the root is 3. So that will be 3 cubed minus 3 into bracket 2 minus 5. Boom, this is 16. Okay, so we have a positive value. So we can assume this root. So it means the root lies between 2 and 3, okay? So when x is equal to 2 or when x is equal to 3. So this is one good place to start. So by regular Falsi, S2 will be the same as S0 minus S1 minus S0 over f of x1 minus f of S0 times f of S0. Okay. Now, what we now have to do, f of S0 is what? This is now S0, and this is now S1. F of S0 is minus 1, right? Now, f of S1 is 16. So we can plug in all of those into this. We know what x1 and S0 are. So S2 will be the same as 2 minus 3 minus 2 over 16 minus 1 times minus 1. And this will give us 2.0588. So it means that within this pool of 2, 3, there's also a point at 2.0588. So we can now consider that point as our next point. Okay, so we also want to check. Let us plug this into the expression, into this. So what do we get? So it means f of 2.0588 will now be 2.0588 cubed minus 2 into bracket 2.0588 minus 5. This will give us negative 0.3908. So it means that on this scale where we have 2.05883, this gave us negative, this also have given us negative, this is positive. So we can now iterate between these 2 points. Does it make sense?
Yes, sir.
Yeah. And once we do that, we now have S3 being the same as S0 minus X1 minus S0 over f of X1 minus f of S0 times f of S0. So we already know what our S0 is now and what our X1 is. And once we do this, so this is going to give us 2.0588 minus 3 minus 2.0588 over 16 minus 0.3908 times minus 0.3908. And this is going to give us 2.0813. Okay? And then we can go on and on and on and on and on, plug this in and see and all the way. Okay? Now, that's that for the regular forces. So let's quickly jump into the open methods and see how far we can take it. We see how just a few minutes. Now, for the fixed point, let's look up fixed point.
Doctor, sorry, sir.
Go ahead.
For the sake of our exam, is it possible for us to maybe probably give us a point at which you are going to iterate to?
We'll talk about exam after lecture, so nothing to worry about yet.
Yes, sir.
Yeah, I don't think you should worry about exam yet. So let's just understand the concepts, then I think we are fine. Then for exam, we'll discuss it. Don't worry. Okay? Yeah.
Thank you, sir.
I think exam should be the list of your worries now, okay? Yeah, x squared minus. You guys have written a lot of exams, so I can imagine grandfathers here now. What exam should you be scared of? Life's exam is the toughest, and you've succeeded that, so there's no problem, okay? So let us look at this. So now we want to figure out a way we are able to use this expression for iteration, and we know this should be equal to 0. So we want to represent this in such a way that we have x of n plus 1 equal to something, and that this equation should do that. So for the fixed point iteration, we want to rework this model. And one way to do that is to say x squared minus x minus 1 is the same as 0. So this is the same as saying x squared is the same as 1 plus x, right? And now we can literally rework this. We can say this is the same as saying x plus 1 over x is equal to x, right? Because if I should cross this, that would be x plus 1 is the same as x squared.
By x. Yeah.
Yeah. So I can say x over x plus 1 over x is the same as x. So 1 plus 1 over x is equal to x. Right? So I can say xn plus 1 is the same as 1 plus 1 over xn. I just performed a little magic, right? For the fixed point. So this is what we are going to use for the fixed point iteration and begin to vary this value, okay? So we want to find the root at which the following equation will converge. So here we want to assume x1 to be some value. It can be anything. So let's assume x1. If x of 1 is, say, so x1 will be the same as 1 plus 1 over when, so we already have, okay, now say, what do I want to do now? What do I want to do now? So I'm assuming x1 to be some value. So let's just say it's 2, for instance. So s2 will be the same as x1 here, right? So that this will be the same as 1 plus 1 over 2, which is 1.5, right? So that's s2. So let's make this nicer. xn plus 1 is the same as 1 plus 1 over xn. So now I'm assuming x1 is the same as 2, so that when n is now 1, that's s2 will be the same as 1 plus 1 over x1, right? 1 plus 1 over 2, which is 1.5. So when s2 is now 1.5, so what will be s3? That will be 1 plus 1 over 1.5. So this will give us 1.6666. Then x3 will be the same as 1 plus 1 over 1.6666 all the way. And this is going to give me 1.6. And then x4 will be the same as 1 plus 1 over 1.6. This will give me 1.625.
That's x5.
Yeah.
The
That should be x5. The one is x4.
No, okay, this is S4.
X4.
S5, yeah. Then X6 will now be 1 plus 1 over 1.625. So this will give us 1.6125. So let's see if what our colleague just mentioned, if we'll be able to get convergence where the answer will now remain the same. So then X7 will now be 1 plus 1 over 1.6125. So what do we get? 1.620. Then X8 will be 1 plus 1 over 1.620 is 1.617. Then X9 will be 1 plus 1 over 1.617 to be 1.618. Then X10 will be the same as 1 plus 1 over 1.618. And this will give us 1.618. I think it just converged. So we can say that the root is X is the same as 1.618. I think this is the concern you mentioned earlier. Are we good? Mm-hmm. So here we are able to come to convergence to say, well, we are good to go. So now, do you have about 10 minutes to spare so I could run through the remaining three techniques, or you do that in your spare time?
Go ahead, sir.
Okay. Thank you.
Go ahead, sir.
Please go ahead.
Okay, thank you. So now we have Newton-Raphson method. So in this case, say we have x cubed plus 2x minus 2 is the same as 0. And here we have two roots defined, x having roots between 0 and 1. So we want to find the root to some decimal place using the Newton-Raphson's method. But we already know that the formulation for the Newton-Raphson's method is such that the approximation is the same, or the approximate value is the same as the initial value minus f of xn over the first derivative of f of x. Now, we already know from this that f of x is the same as x cubed plus 2x minus 2. So we can tell the first derivative to be 3x squared plus 2, right?
Yeah.
So now if that is correct, then we can figure this out now. So we already know what x1 is, right?
Yes, sir.
So we can tell our next point. Okay, so this is S0, this is x1. So we want to figure out the next point. So it means that S2 will be the same as x1 minus f of x1 over f prime of x1, right? So this now will give us x1 minus this expression, f of x cubed 1 plus 2x1 minus 2 over 3x squared, that's 1 plus 2, right? Yeah. So we can plug in the values for x1 because we already know that x1 is the same as 1. So this would be 1 minus 1 cubed plus 2 into bracket 1 minus 2 over 3 into bracket 1 squared plus 2. Okay? And once we resolve this, this should give us S2 to be the same as 0.8. Now, we now have to repeat the same process to evaluate S3. Now, S3 will now be the same as S2 minus f of S2 over f prime of S2. Okay? And we already know what S2 is, which is 0.8 minus 0.8 cubed plus 2 into bracket 0.8 minus 2 divided by 3 into bracket 0.8 squared plus 2. And this is going to give us 0.77 142. Okay. So we are literally moving from 0.8, scaling down to 0.77. So we can also figure out S4 will be X3 minus F of X3 over F prime of S3. And this is going to give us S3 is 0.77142 minus 0.77142 cube plus 2 into bracket 0.77142 minus 2 over 3 into bracket 0.77142 squared plus 2. And now S4 is going to give us 0.7709. Now, we just got this, so we want to figure out the next point to see if it will converge, right? So let's evaluate X5. Should be X4 minus F of X4 over F prime of X4. And this is going to give us 0.7709 minus 0.7709 cube plus 2 into by 0.7709 minus 2 over 3 into by 0.7709 plus 2. And S5 once again is 0.7709. So we can say that 0.7709 is the root, okay? And here you see that since our previous assumption of S1 was 1, now you recall that X lies between 0 and 1. So what if we put X to be 0.5, for instance? Are we going to get the same result? I don't know if you get what I mean. So here, our point is, this is what we have, right? And we assume that our first initial guess to be 1. What if our initial guess was somewhere in between this interval? Let's say half of it, 0.5. What are we going to get? So you see that regardless, what we got here using the Newton-Raphson's method is this 0.7709, which is within the interval. And now 0.5 is also within that interval. What if our initial guess was some value other than 1? Are we sure it will converge? We can try it. Let us see. So now it means that S1 is 0.5. We use 1, right? So let's see. S2 will now be 0.5 minus 0.5 cube plus 2 into bracket 0.5 minus 2 over 3 into bracket 0.5 plus 2. And this is going to give us 0.81. And now X3 will now be 0.81 minus 0.81 cube plus 2 into by 0.81 minus
3.05 square. 3 times 0.5.
What's that?
Oh, this one, 3 multiplied by the bracket 0.5 square.
Yeah, we are just making an assumption. You know, we took our x1 to be 1. So
what he's saying is 0.5 squared, the denominator of x.
3 times 0.5 square.
Denominator.
Okay, this squared, right?
Yes.
Okay. That's what we have for our equation, right? Is that what we have for our equation?
Yes, sir. Yes, sir.
Yes.
Yeah. That's true. Now, so by the time we figure this out, you solve that and let's see if we are consistent. Then these two will be 3 into bracket 0.81 squared plus 2. And then this should give us for X3 0.7722. And then for S4, we have 0.7722 minus 0.81 Q plus 2 into by 0.81 minus 2 over 3 times 0.67, sorry.
Yeah, that's
0.77.
Yeah, 0.7722, 0.7722. This is why you don't want to attempt this with your hands, right? 22 plus 2. So this should give us 0.7709. So I think we are where we stopped earlier.
Yeah, this is that x is supposed to 4. I mean x4, sorry.
So my apologies for that, that was a little distraction. So I think now we want to try for x5, which would be 0.7709 minus 0.7709 cubed plus 2, 0.7709 minus 2, 3, 0.7709 plus 2. And that equally gives us 0.7709. So the bottom line is the Newton-Raphson's method converges so long the initial guess is within that range or interval. I don't know if you get what I mean.
Yes, sir.
Yeah, so, well, sorry for that. The call came in because my class is as good as over. And that's supposed to be another appointment. Okay, is there any other method we have not mentioned? Okay, the secant method.
Secant.
Okay, so let us look up the secant method. So let's assume
And the Muller.
Okay, is the same as 20. So after 2 iterations given the initial, want to find this, let's just do 2 iterations for this. And here we are given the initial guess of S0 being the same as 4, and then X1 being the same as 5.5. Okay, so what we now have to do is that X cubed, we have X cubed being the same as 20. So we have to equate this to 0 so that X cubed minus 20 is equal to 0. So that's our f of s, right?
Yeah.
So that Sn plus 1 will be the same as Sn minus f of Sn, Sn minus Sn minus 1 over f of Sn minus f of Sn minus 1. Okay? So we already know S0. And so let's say if we already have S0 X1, so S2 will be the same as S1 minus f of S1. This would be X1 minus S0, right? That's 1 minus 1 over f of X1 minus f of S0, right? So this means from this that S1 is 5.5, 5.5 minus f of S1. That will be, we plug in this equation, x cubed minus 20. So that will be 5.5 cubed minus 20 times x1 minus S0, 5.5 minus 4, 5.5 minus 4. Then everything we divide through f of S1 again, so that will be 5.5 cubed minus 20 times, okay, minus f of S0. So when we plug in 4 into the same equation, so that will be 4 cubed minus 20. Okay, so here S2 will be the same as 3.353. So we just want to perform 2 iterations, right? So it's the same process. So that X3 will be the same as S2 minus f of S2 into bracket S2 minus S1 over f of S2 minus f of s1, right? So we can now plug this in. Our s2 is the same as 3.354 minus f of s2 will be 3.353 cubed minus 20. Then we multiply again by S2 minus S1, 3.35 minus S1 is 5.5 over f of S2, that will be 3.353 cubed minus 20 minus x1, when f of s1, so that will be 5.5 cubed minus 20. And this is going to give us 3.059. So we can go on and on and on and on till it converges. Yeah.
For the S3 is equal to S2.
What's that?
So for the S3, so when we are plugging in, we made a mistake of 3.354 instead of 3.5353.
3.353. So did I use 3.354 anywhere?
Yes.
Yeah, please tell me. 3.353, 3.353.
For the S2. For the S2 at the beginning.
Okay, yeah.
the X2.
Yeah, it's 3.353, please, not 3.354. Because it's S2. It's S2. So yeah, corrected. Yeah. Yeah, 3. It's 3. So I think this can also go on and on till convergence. I think this now the methods of finding the roots to the equation or to the nonlinear equation is pretty straightforward, isn't it?
Yes, sir.
Yeah. So let's look at the Muller's method, and then that will be it for today. So let's assume we have f of x. So here we want to look up the Muller's method. Though this is a little computationally intensive, but it's the same thing, okay? So x cubed minus x minus 1. And here we have the initial estimates, S0 to be 1, S1 to be 1.5, and S2 to be 2. And you know, here we are playing with quadratic polynomial. So, and most of your models will definitely run into some kind of polynomials of some degree n, and we always want to constrain to, you know, the quadratic or better still beyond that. But whichever way, this is just fine. And here, let's say we define the tolerance to say this to be the same as 10 to the power of minus 6. So once we get something close to this tolerance threshold, then convergence, we should, the iteration should terminate, right? But if it should converge before that point, then that's fine, you know. So now what we have here is that f of x is the same as x cubed minus x minus 1 being the same as 0. Okay? And we already have these values, S0, S1, S2. So we want to compute the differences, right? And you remember that we said H1 is the same as S1 minus S0, which is 1.5 minus 1, which is 0.5, right? So
H2.
Then H2 will be the same as S2 minus S1, which is 2 minus 1.5, which is 0.5. Now, the next thing we need to compute will be f of S0, f of S1, and f of S2, right?
Yeah.
So we want to do this. So this will be f of S1, that will be 1 cubed minus 1 minus 1. This is going to give us negative 1. And then 1.5 cubed minus 1.5 minus 1 will give us 0.875 because S1 is 1.5. Then S2 is 2. Then we say 2 cubed minus 2 minus 1 will be the same as 5, right? So we literally evaluated these. Then the next thing is to evaluate the difference, right? So delta 1 will be the same as f of S1 minus f of S naught divided by S1 minus S naught, right? So this will give us 0.875 f of S1 minus f of S naught minus 1 minus 1 over x1. S1 is 1.5 minus S naught is 1, right? So once you do this, so delta 1 will be the same as 3.75. So we want to do the same for delta 2, which will be f of S2 minus f of S1 over S2 minus S1. So this now will give us delta 2 being the same as 5 minus 0.875 over S2 minus S1. We already did that. S2 minus S1 will be 0.5. And this is going to give us 8.25. So now that we have the values for delta 2, delta 1, and the like, so we can now evaluate the coefficients, A, B, C, right? So we know that A is the same as delta 2 minus delta 1 over H2 plus H1. So this would be 8.25 minus 3.75 divided by H2 plus H1, 0.5 plus 0.5.
As 1.
So this will give us 4.5. So we know what A is. And now B is the same as AH2 plus delta 2, which will give us 4.5 times 0.5 plus 8.25. Delta 2 is 8.25. So this will give us 10.5. So what is C? C is the same as f of S2, right? Which is 2 to the 2 cube. I think we already did that. Minus 2 minus 1, which is 45, right? C. So now, what do we need to do? We need to compute the next approximation. Okay? And for us to do that, we need the D value, because the next approximation is going to be x whatsoever minus 2c over the quadratic notation. And depending on the value of D, then that will tell us if it will be, if I want to use the positive or the negative. But that's fine, don't worry, we'll become clearer. So now let's compute the next approximation, but we know that D is the same as square root of B squared minus 4AC. So what do we get here? This will give us 10.5 squared minus 4 times 4.5 times 5. So this is going to give us 110.25 minus 90, right? Which will now give us square root of 20.25, which is 4.5. So D is the same as 4.5. Now, what we will now do is this. Now that we have done this, recall that A is 4.5, B is 10.5, and C is 5. Okay?
Yeah.
Now, in this case, you see that our B is positive in this evaluation. Right? Now, what if B was negative? We are not going to choose the option we choose now. Okay? Now, since B is positive in this case, then it means that we are going to choose B plus D as our denominator. Okay?
Okay. Okay.
So let me clear this. Oh, no. Let's come back. I just need to clear this. I think I should write that down. It's an important point to note. Now, since B is positive, we will choose the denominator as B plus D, okay? Because S2 will now be the same as, no, S3 rather. We already have S0, S1, S2. So we are evaluating X3 will now be the same as S2 minus 2C divided by the denominator, which would be B plus D in this case. Okay? So because B is positive, going by this, that is why when we use the Muller's method, we can literally have complex roots. Because if we should have square root of -1, then this is the same as J.
Yeah.
And Newton-Raphson cannot do this. That's one advantage of the Muller's method. Okay? But now it is positive, so this is what we get. So by the time we substitute all of these, then we are going to get our next approximation, which will be S2. We already know S2 to be 2, right? That's given, minus 5, 2 over 5. C is 5, right? 2 times C, that's 2 times 5 over B plus D. So we know what B is. That's 10.5 plus 4.5. And this is going to give us 2 minus 10 over 15, right? And then it means S3 will be the same as 1.3333. So we know our next point. So this is where the struggle begins. So we know our S3. Now we need to test for convergence. S3 is the same as 1.3333. But we also know S2. What's S2? S2 is 2. So for us to check convergence, so we now need to check for convergence. Because we're given tolerance, right? E
yes, sir.
is the same as 10 to the power of -6. So let us see if our error threshold is within that range. Then if it's not, then it means we have to iterate again. Okay? So now it means I will have to figure out the mod of the difference between X1, X3, and S2. And that will now give us 1.3333 minus 2. Right? Since we are taking the modulus, it's going to be a positive value or the same. 0.6667. Now you observe that 0.6667 is greater than 10 to the power of -6. So we have to iterate again. Does this make sense? Does this make sense?
Yes, sir.
Yes, sir.
Okay.
Yes.
So do we need to play with the second iteration, or is something you can do on your own? Or should we play with
Let's
one?
play with it, sir.
Okay, and then from the third and beyond, you can do on your own. Okay, so now we have some new points, and then we can just establish that. So let us write this. So it means that S0 will now shift, right? Our S0 will now be our previous S1, which is 1.5. And our S1 will be our previous S2, which is the same as 2, because we need 3 points based on the quadratic polynomial. And then S2 will now be our new S3, which is the same as 1.3333. Okay? Now, we already know that H1 is the same as X1 minus S0, right? And this will give us 2 minus 1.5, which is 0.5. Okay? And now H2 is S2 minus S1, which will give us 1.333, our new point, minus 2. And this is going to give us minus 0.6667. Then we now have to evaluate f of s naught, f of s1, and f of s2. And this is 1.5 cubed minus 1.5 minus 1, which is 0.875. And then this is 2 cubed minus 2 minus 1, which is 5. And then this is 1.3333 cubed minus 1.3333 minus 1, which is 0.037. So now that we have evaluated all of these, we know delta 1 will be the same as f of s1 minus f of s0 over h1. And this is going to give us 5 minus 0.875 minus 0.5. So delta 1 will be 8.25, right? And now we can also evaluate delta 2, which is f of s2 minus f of s1 over h2, which will give us 0.037 minus 5. Then h2, in this case, is minus 0.6667, right? And this is going to give us 7.438. So delta 2 is the same as 7.438. Right? Then we can now evaluate A, which is delta 2 minus delta 1 over H2 plus H1, which is 7.438 minus 8.25 over 0.5 plus minus 0.6667. And once we resolve this is going to give us 4.87. So it means A is same as 4.87. Then we can evaluate B to be AH2 plus delta 2. And this will be the same as 4.87 into bracket minus 0.6667 plus 7.438. And this will give us 4.17. And then, we know B, then C is the same as f of S2. I already evaluated f of S2, so that's 0.037. Okay. So now, what we want to do is to compute D, which is the same as square root of B squared minus 4AC, right? And this will give us 4.17 squared minus 4 times 4.87, 0.037, right? So once we resolve that, that will give us 4.08. But now, once again, B is 4.17, is positive. So it means that we have to choose B plus D as the denominator, right?
So what about if it is negative?
Now, if it is negative, then we want to choose negative B, negative D, right? So that negative B plus D, then we are going to have a negative way with J, right? Square root of B plus D, right? Isn't it?
Yeah, I get it.
Mm-hmm. Okay, so let's clear this out. So now we are now going to have so now that we have chosen this,
X3.
and S3 will now be the same as X2 minus 2C over B plus D, right? So this will be 1.3333 minus 2 into bracket 0.037 over 8.25. And this is going to give us S3 to be 1.3243. And once again, we can test for convergence, S3 minus S2. So this will be 1.3243 minus 1.3333. This is going to give us 0.009. Well, it is still less than 10 to the power of minus 6. So we are going to iterate again. No, it's greater. Sorry, this is greater. It's greater, please. It's greater. It's greater. So then we are going to iterate again. Okay. So this process will go on and on and on and on and on till we are able to get our convergence. Okay. So I think this is a good place to
Yeah,
stop.
it's less than
It is well, it is
10,
well.
10 raised to power minus 6, right, sir?
Sir?
Until it is less than 10 raised to power minus 6.
Or well, until it is
Close.
close, yeah, as possible.
All right.
Yeah, because what we end up doing here, we are literally trying to figure out an approximate route.
Yeah.
Okay. So it's not an actual value. So the closer it is, the better. Okay.
All right. Yeah.
All right, sir.
And so that you want to design systems that are as stable as possible, but we know you cannot achieve 100% reliability, right? So you want to achieve 0.99 something or 0.98. Once you're able to achieve 0.999, well, that's fine. That's fantastic, right? So I think that's the idea, okay? Because we cannot really. There are a lot of things that will introduce errors or create some non-linear behavior in the system at the end of the day. So is this a good place to stop?
Yes, sir.
Okay, so do have a great day.
Please, announcement. The student, I was talking about the list I wanted to compile to